Okay, just to grapple with the problem a little bit at first, you have this spherical tank, radius 8 feet, it's half full of oil that has a density of 50 pounds per cubic foot. I know it says weight, but it's saying weight per cubic foot. So that's really a density there and not a force unit of 50. Find the work required to pump the oil out the top of the tank. That's what we're after here. So the first thing I'd want to do is draw a picture. And I know on the worksheet, I said for preparation to draw the equation of a circle or to write the equation of the circle with a center of 0.8. But a student taught me how to do this last year in a way that doesn't use equations of circles at all. It just uses geometry. And I think it's a really clever way to do it. So that's how I'm going to show it. And it sets up the circle more naturally for students, which is like the center being right there. Okay. Now, radius is 8, so all these distances are 8, right? And many more, infinitely many distances are 8 there. It's half full of this oil. So the oil level stops right here, okay? The first step is to make a slice. And when you make your slice, make sure you make it in a random spot where the fluid is. So the fluid is only down below. So don't pick right in the middle, don't pick at the top, and don't pick at the bottom. Just pick a random spot where you're going to slice the oil. Really, really thin. And that thinness I'll call delta Y because I kind of got it set up and down. Okay. Now this isn't 2D, this is a side view. The tank is 3D. So this object, this slice, is not a rectangle. It is a cylinder. And I know that its height is delta Y. Now, the only thing I can do with the cylinder is get that volume. So I'm going to begin with the volume of the slice, or delta V. And that is a cylinder, so it would be pi radius squared height. And I know my height already is going to be delta Y. What I need is my radius. Okay, I'm going to highlight the radius of the cylinder here and here so you can see it. Okay, and that radius is an x value. And this distance right here, we might call y. Or better yet, let's think about it. This is 8, right? That distance right there is 8. It's a radius. This distance is 8. And if I make the distance to the bottom of the slice the y, let y equal the distance slice to bottom of the tank. It's a variable distance, right? Then this distance right here, this leg, is 8 minus y. So if I want to find x here as a radius, I'd love to put it right here as x, but I can't because I made a decision in terms of y. So what goes here is x in terms of y. And my geometry tells me I'll blow up this situation. I have a right triangle with this leg 8 minus y, this leg x, and this leg 8. So x squared is equal to 64 minus 8 minus y, the quantity squared. I'm just using a squared plus b squared equals c squared. Pythagorean theorem. So that's what x squared is. I can square root it to get what x is. No square rootedy root, please. That's what it looks like. I'm going to turn around and square it, though. So it's the square root of 64 minus 8 minus y quantity squared. So what I have for my volume of my slice is pi 64 minus 8 minus y quantity squared delta y. And that's volume. Now, it was squared times another. So it was square feet times more feet. So the units on this is feet cubed. And that is not force. So to go from volume to force of a slice, Typically what you have to do is multiply by G and also multiply by density. But in this case, you're not going to have to multiply by G because you have 50 pounds per feet cubed as your density. So if I multiply by pounds per feet cubed, I'm going to get pounds, and pounds is most certainly a unit for slice, for force. Newtons is as well, right? But we have pounds. So my force slice, I'll write that as delta F, would be pi 64 minus 8 minus y squared. Delta y times 50. Now that's force. Now it's time to go to work. To go from force slice to work of the slice, work is force times distance. So I'm now going to multiply by the distance. And the distance I mean here is the distance to done, whatever done is. In this case, done is to take that slice out the top. So to take that slice out the top, I'm going to do 8 plus 8 minus y. And that's 16 minus y. That would be my distance to done is 16 minus y. So my delta work is, I'll just put the 50 in front, 50 pi 64 minus 8 minus y, the quantity squared, delta y times distance to done, which is 16 minus y. That's my work slice. The limit of the Riemann sum of infinitely many of those will give me my total work. And I have quite a bit of constant that I could put in the front. I've got 50 pi I can put in front for my total work. And then I have 64 minus 8 minus y, the quantity squared, times 16 minus y, and my delta y turns to the dy that I need to integrate. Now, the only thing left is to give me y values for the integration. Now, remember that I defined my distance, my y, to be the distance sliced to the bottom of the tank. So the slices are either at the bottom of the tank, 0, or they range to 8 above the bottom of the tank. So I'm going to run those from 0 to 8. So I have to expand all of this and multiply it out. Super fun. If I was going to do it by hand, it'd be 64 minus 64 minus 16y plus y squared. So that's kind of nice because the 64s will cancel. And what I have here is 16y minus y squared times 16 minus y dy. And I could expand that. This is like another time I did this. So if I expand that, I would have 16 times 16 is 256 y minus 16y squared minus another 16y squared. Yeah, minus another 16y squared. So that's minus 32y squared plus y cubed. Yeah, right? Yeah. So it ends up being like pretty easy to integrate by hand. And if I didn't have my calculator, that's what I would do. 256 times 8, I get 2048. Oh, wait, no, wait, I'm trying to integrate here. So 128 y squared minus 32 thirds y cubed plus y to the fourth over 4, that between 0 and 8. So that's 128 times 64, which is 8192, minus 32 times 8 to the third over 3. Plus 8 to the fourth over 4. Which is 1024. And if I add all that up, multiply it out, et cetera, I end up getting 50 pi times 11 to 64 over 3, or approximately 589,782. And that would be foot pounds when I do a unit analysis of what's going on here. I've got my force units right here are, my force units, remember, were in pounds, and I was multiplying that by feet. So all of this was pounds. I was multiplying that by feet, by distance. So it's foot pounds.